morning, everyone. I'm proud to present our paper, Frustum Volume Caching for Accelerated NeRF Rendering. First, let's give a quick introduction to NeRFs. You heard of them yesterday already, but in general, they are used to solve the inverse rendering problem, which means to learn a 3D scene representation from a set of 2D posed images. And this can be used to render then views from before not seen viewpoints, so novel view synthesis. The original NeRF paper from 2020 used differentiable volume rendering, ray marching, and evaluating a network for each sample with input a 3D sample position and view direction, and the output being outgoing radiance, so color and density. And accumulating this up per ray and comparing it to the ground truth image allows you to learn this representation. The underlying network they used was a large MLP, and this led to very large training times and far below real-time frame rates. A quick background of so this introduced many follow-up works. Most important for us will be MIP-NeRF 360, which is an anti-aliased NeRF method. So instead of evaluating infinitesimally small samples, they evaluate Gaussian blobs. They also performed scene contraction in order to handle unbounded scenes, warping them into a bounded domain, and introduced a distortion loss, which encourages the NeRF to form proper surfaces and consolidate density along the rays. Another important follow-up work was Instant NGP from 2022 by Miller et al., who introduced a multi-resolution hash encoding, which proved to be much more efficient in encoding 3D positions than the previously employed frequency encoding with large MLPs, and allowed to use much smaller MLPs, which led to much faster training times and rendering times as well. What they also employed was binary occupancy grids, which are commonly used for empty space skipping and which are also optimized during training. A quick background, the key takeaway is that previously potentially all NeRF methods employ networks that are split into two parts. The first base network is pretty expensive usually and extracts a view-independent latent code. And the much smaller head network then gets also fed the view direction and outputs view-dependent color. So this acts as a first motivation for our method, as we want to cache these view-independent outputs to reuse them across consecutive frames and reevaluate only view-dependent effects. Some background and related work. Previous methods tried to accelerate NeRFs by either baking them into a more render-friendly format, so training a high-quality NeRF model, and then, for example, SNERC bakes it into a sparse voxel grid with neural features which can then be more efficiently queried than, for example, a large MLP. Other methods like mobile NeRF extract a mesh from a trained NeRF model, which can then be efficiently rasterized or ray traced, like we heard yesterday. This usually has the problem that it struggles with thin structures and semi-transparent surfaces. More closely related to our method, FastNeRF attempted to accelerate it by splitting the NeRF into two completely separate networks and caching only view-independent codes in world space. This was only done for the original NeRF network and only for very small bounded scenes. Some other related work in the field of temporal coherence methods, more specifically volumetric ones. Image-based techniques rendered layered images, which could then be efficiently rendered using image-based rendering techniques. 3D irradiance probes were used to cache 3D irradiance in world space. More recent methods like neural radiance caching use coordinate-based MLPs to use temporal coherence also in world space. And more closely to our method, view-aligned caches employed Frustum voxel or froxel grids, for example, by Vronsky and Hilaire, to cache irradiance of participating media like fog. So to come back around to our task of caching NeRFs, the general idea of our model is to cache the view-independent output of the base network in a view-aligned voxel grid. This cache can then be sampled from nearby viewpoints to re-evaluate on a view-dependent color through the considerably smaller head network. This comes with a couple of important challenges to keep in mind when designing our method. Firstly, we'll have to be able to detect cache hits and cache misses on a per sample basis, and then also to blend these cache misses and hits along rays. Another challenge is to keep cache size reasonably small. This can be achieved by reducing the size of latent codes and using sparse data structures. Also, we require fast cache initialization so that our method can also be used for real-time applications, and critically, of course, fast cache lookups and color re-evaluation, so otherwise our method would not make sense. And of course, we have to be able to properly interpolate samples from cache without introducing any aliasing artifacts. So let's get straight into how do we interpolate these NeRF samples. Our cache consists of 3 separate 3D voxel grids storing latent codes, density, and binary occupancy information. In general, we initialize all unoccupied cells to 0, and when sampling density from this cache, we first transform any 3D sample point into voxel space and trilinearly interpolate from our density voxel grid. This leads to no problems, as these unoccupied cells are just treated as having a density of 0. For latent codes, we have to account for this potential 0 shift by normalizing using the occupancy information. The problem in general is that the latent codes are the output of a highly nonlinear function, so a neural network, and interpolating them linearly might not give meaningful results, even for spatially close 3D samples. And to see what would happen if you naively interpolate them is here, where you see these streaking artifacts and white dots. So to induce spatial linearity during training, we shift training rays by a random stepping offset in Z direction and interpolate each actual sample from 2 shifted samples. If one of those samples is outside the occupancy grid, its interpolation value is set to 0. And this behavior effectively simulates the same interpolation scheme later employed during cache retrievals. One unnecessary property of latent codes is that they are completely view independent, meaning they can be re-evaluated from a whole 360-degree viewing angle. For our temporal coherence method, however, we will only ever encounter small view changes. We therefore choose to limit latent codes to only be valid inside a cone up to a certain angle, here 22.5 degrees, so encoding a 45-degree cone overall. This has the advantage that latent codes now can be smaller, as they have to be less informative, and head networks can also be smaller due to the same reason. So, in more detail, our cone encoding produces latent codes which were generated from a view direction VC, but can be re-evaluated from a similar view direction VT lying inside the same cone of some maximum angle, theta max here. This encoding can be learned during training by carefully choosing a number of view directions, 4 in this case, and providing the difference in viewing angle to the head network and averaging the final loss of all samples. And this way, we effectively shift some computational load from the head network to the newly introduced neck network. Finally, we propose a full model which is especially suited to our caching and reprojection approach. It is based on instant NGP, but the base output is directly fed into the neck network of our cone encoding. Density is still entirely view independent, as this is essential to obtain view consistency. This now introduces latent codes which are somewhat view dependent and are only valid inside a cone around VC. Now that we are able to properly perform lookups from our Frustum grid, let's have a closer look at the employed data structures. As we already said, to reduce cache size, we want to have sparsity in our data structure. Therefore, we use sparse Frustum grid with fixed-sized bricks, for example, of size 8 by 8 by 8. And they are essentially split into two different data structures. One storing brick information, so occupancy, and indices, which point into the data array where the actual per sample data, so occupancy, density, and latent codes lie. Importantly, neighbors in B are not necessarily neighboring in D. They're needing some form of interpolating across brick borders. During initialization, we choose to perform brickwise initialization to fully utilize the reserved memory, and optionally we pad bricks to also store neighboring information, simplifying the trilinear interpolation so we don't have to care about brick borders. For reprojection and sampling, we perform normal ray marching and per sample check first the global occupancy grid. If it's not set, we always reject samples. A cache miss happens only if a sample is also outside a known range, which we built during cache initialization and which is valid between the cache camera's near plane and the termination depth of its individual rays. Cache hits only happen if our sample is inside this known range, if both brick and data arrays are set, and if the sample we trilinearly interpolate has high enough density. And all these checks enable us to have as few as possible false cache hits, and thereby reducing the number of unnecessary evaluations of the head network. Some quick implementation details. Our network is trained in a training framework based on PyTorch and based on the NeRF framework. Our real-time viewer and offline renderer is implemented in C++ CUDA and uses tiny CUDA in N for hash grid encoding and MLP evaluation. Importantly, although tiny CUDA in N is quite fast, all the additional encodings of our head network require us to use a custom fused GPU kernel that performs all these operations in a single kernel. And to get to our results and evaluation, we evaluate on the MIP-NeRF 360 dataset, which contains challenging indoor and outdoor scenes, and they capture 360-degree viewing angles with some central object of unbounded scenes. The models we compare against are a larger base variant of instant NGP without any further changes. A adapted version of instant NGP which employs scene contraction, distortion loss, and also has interpolation training, which we can also use for caching and reprojection. Our method, which also uses the cone encoding with a maximum cone angle of 25 degrees, and which also uses smaller latent codes and head networks. And to show scalability of our approach, we also use a model, an instant NGP model, with an even larger hash grid. Here we show model quality for base instant NGP model and ours, and we see that scene contraction and distortion loss lead to a significantly higher PSNR score, and also to drastically reduced sample counts, which translates directly into better performance. Compared to other novel view synthesis models, we simply show that we can achieve competitive results in both indoor and outdoor scenes. So in order to evaluate performance and quality of our cache renderings, we render the cache from the dataset test set viewpoints and only move the cache initialization viewpoint around its vicinity. We do this for rotational viewpoint changes, for different degrees of rotational change. Here you can also see the corresponding cache hit and cache miss masks. And we also perform the same evaluation for translational movement along the view ray. So in terms of performance, we can quickly see that our approach is much faster than instant NGP due to the much lower sample count, and that our view encoding introduces no additional overhead. Looking at cache performance, we achieve large speedups when rendering from our cache, but we can also see that as the cache hit rate degrades for larger viewpoint changes, also our speedups decrease with it. Instant NGP, on the other hand, the base model is unsuited for caching and achieves almost no speedup as the head network is simply too expensive to evaluate. Additionally, cache size is smaller for our base model as we use fewer latent codes, and using the same latent code size with instant NGP also doesn't lead to significant improvements in cache rendering performance. In terms of quality, our modifications enable high quality rendering from cache. As we can see, the instant NGP variant does as well, but here, of course, we saw that we couldn't get any performance benefits. We also see that we can faithfully render from cache when we employ even smaller latent codes. And here we see that our approach fails considerable when we do not induce spatial linearity during training. So here for rotational view changes, PSNR degrades from 30 to 24 PSNR. If we train our view encoding for smaller viewing angles, it fails to reconstruct the cache for large rotational view changes, as seen here. We also evaluated a video sequence to showcase the capabilities of our model for a 300 frame video path for predefined cameras for several scenes. And to show scalability, we used the huge variant of our model. We also employed super sampled volumetric motion blur and depth of field, which further fits our model as we can sample the same cache very many times for similar viewpoint changes. And here you can see our caching approach achieves almost indistinguishable results from the baseline with a significant speedup of 1.8x. Importantly, in these 1.8x, the cache initialization times are already included. We perform automatic cache updates as soon as the viewpoints change too significantly or if cache hit rate decreases too far. The small spikes that can be seen here are due to cache hit rate decreasing and thereby performance decreasing, and as soon as the cache is reinitialized, performance is back to normal. So some conclusion, limitations, and future work. One limitation are currently large cache sizes, which make our method not suitable for lower-end graphics devices. The 3.4 gigabytes were for full HD resolution. Cache initialization is also a problem and would require significant latence hiding for real-time applicability. For offline rendering, this is of course not a problem. And our method is still slower than explicit methods, for example, meshes or 3D Gaussian splatting, while while not suffering from some of their downsides, like popping artifacts for 3D Gaussian splatting. Concerning future work, it's desirable to further reduce cache size, for example, by compression or hierarchical consolidation, so combining similar spatial latent codes inside the cache, and applying our method to VR applications where we can essentially reuse the same cache for two viewpoints. In conclusion, we are able to accelerate NeRFs by caching and reprojecting NeRF latent codes. We employed a fully view-aligned, fully volumetric cache and are able to re-evaluate view-dependent effects successfully. Also, our method enables high quality and fast offline as well as real-time rendering. Thank you for your attention. Our source code is public on GitHub, and please visit our project page for more information.
Thank you, Michael. Really good speed ups. While we're setting up the second speaker, do we have questions in the audience about this work? Maybe I can start with one. I know it's probably out of the scope of the work, but how would you compare in terms of the performance and memory footprint your method to Gaussian splits?
Yes, I think in terms of model size, instant NGP models, except for the very huge variant, compare quite well. So Gaussian splitting models can be exceptionally large. But in terms of memory footprint during rendering, Gaussian splitting is pretty efficient. And in terms of rendering times, also most NeRF models, except for the most efficient baked methods, can't compete really at the moment.
I guess as a follow-up, have you considered combining the best of two?
We tried a forward reprojection method that would probably go a similar path, but in the end we switched back to a backward reprojection process because it allowed us for better cache misdetections and filling in missing information inside our cache.
Thank you. Any other questions in the audience? Oh, yeah.
Yes?
Do you have to do any compensation for the variable length of the cache regions?
Can you repeat that?
In voxel space, your cache regions are not of uniform length. Do you have to do anything to compensate the areas represented by cache?
So we use a regular Frox. I think the question was if our Froxel grid is if it is irregular or.
Well, as you get further out in the space, each voxel represents a larger volume. So the non-uniformity of the regions that are being represented in the cache, you have to compensate.
Yes. So essentially, our Froxel grid lives in a space where the Z coordinate is the index of the stepping space. You can read more in the paper, or we can talk about it afterwards. Essentially, yes, regions that are further away from the camera, we use exponential stepping, so we use larger and larger step sizes. And then by bringing it back into the stepping space, this contracts basically the space again, so you can properly trilinearly interpolate. I hope this answers the question.
Any other questions?
Yes?
Is there any disocclusion error? So usually the projection solution based on kind of forced projected errors kind of
So the question is if we encounter any problems due to disocclusions. And this is the nice thing of our method, as we perform per sample cache hit and miss detections, and as we know the exact known range of our cache, where we should have information, we are able to then resample with the help of the global previously defined occupancy grid and fully get rid of any disocclusion problems. You can also try out our code, the real-time viewer, where you have a nice visualization of rendering without evaluating cache misses and with evaluation. That should also be in the supplementary video.
All right, let's have some time for the next speaker. Meanwhile, let's thank Mikhail again.
Thank you.